Hi, you guys. We are still looking at reaction mechanisms. So remember, reaction mechanism is kind of the steps that a reaction takes to go from the reactants to the products, and we can use it to determine the rate law. So yesterday we worked on a slow initial step. Remember, the slow step is the rate determining step. It's the step that's like, whoa, this is gonna be how fast the process will go. Next, we're going to work on a fast initial step. And the fast initial step, the process to get this is a little bit trickier. And it's going to be a little bit trickier because of the intermediate. So we'll see what I mean in a moment. So we're going to work with this equation first. So two nitrogen monoxide gases and bromine gas combine to form two NOBr. So the rate law for this reaction is experimentally found to be this one here. So we can see that a 2 here, a 1 here, this is a third order process. Which means if this was an elementary step, it would be a molecular process. And so a molecular, the means 3. In order for this to happen, 3 molecules would have to line up perfectly. They would have to orient perfectly. They would have to have the exact right amount of activation energy. And that is super unlikely to happen. And so when you see a third order process, most of the time it's going to be a multi-step process. So let's look at the proposed mechanism. Now, the reason that these are all proposed mechanisms is that intermediate molecule comes and disappears super fast. And so it's really hard to measure intermediates. It's super easy to miss an intermediate. So this is what we think is happening, most likely is happening, but we could always be proved wrong as scientists. Okay. So step 1 includes the forward and reverse reaction. So we can see that it has this kind of double arrow here, which means that this reaction is going forwards and it's going backwards, which is going to be helpful for us as we're finding our rate determining step. Okay, so when we, let's just double check that this is going to get us to the right equation. So I see the NOBr2 cancels out. So that is our intermediate. We form it in the first reaction. We get rid of it in the second reaction. So we're left with 2 NOs, Br2, and then 2 of the NOBRs, which is what our original equation was. Now we notice here the slow step comes second. So this is the rate determining step. Okay. So put this all together, if we were to write the rate law for the rate determining step, it would look like this. It would be the NOBr2, which we said was the intermediate, and the nitrogen monoxide. The problem is that is an intermediate, which means that we know it disappears very quickly. We actually have no way of measuring its concentration. And in order to use this rate law, we have to know the concentration of that thing. And so we are going to have to do some work here to substitute in what we do know for the part that we don't know. So let's go through that. So NOBr can react in 2 ways. It can react with the NO to form the NOBr by the equation that we saw. That's the slow step. But it can also be by decomposition to form the NO and the Br2. So this is the reverse of the fast step. Okay, so the reactants and products of the first step are in equilibrium with each other. We saw those double arrows. That means that the rate forward and the rate in the reverse are the same. So remember, when something is at equilibrium, and our next chapter is all about this, something at equilibrium doesn't mean the reaction stops. It means that the forward and the reverse are happening at the same rate. So every time I make a product, I'm also making a reactant. This is going to be super helpful in determining our law. Okay, so because the rate of the forward and the rate of the reverse are equal to each other, this is the rate of the forward for our slow step. And if we reverse it, this is the rate, not our slow step, our fast step. This is the reverse of the fast step. So when we rearrange, we can get that NOBR2 by itself, which is that unknown piece in our rate law. So when we rearrange, we get rid of the K minus 1, we divide by it, and we end up with this here. This is going to be combined to just be K. Okay, and then we can plug that in to where we had the NOBR. So where we had our rate law of rate equals K NOBR2 NO, and this was the one we needed to get rid of. We can plug in for that our expression from our fast step. And then when we simplify, our NOs can go together. So it's NO squared BR2, which is what our initial prediction was based off of the data. Okay, let's go through this whole process again. I'm going to try and keep it on one screen so that we can see exactly what's going on here. So here we have a proposed mechanism for a reaction, and we want to show that the following mechanism for the equation is consistent with the observed one. So this is our ultimate goal of what we want to get, okay? So let's look at what we've got here. So our slow step is the rate determining step. Okay, so if we're just using the rate determining step and it's an elementary process, we can write the rate law from the balanced equation. So our rate is equal to K N2O2 and BR2. Okay, simple, right? Now the problem is though, N2O2 is a product in the first, a reactant in the second, so that is our intermediate. Okay, so we have absolutely no way of knowing that concentration, and so we cannot use that rate law. We have to get the N2O2 out of it in order to use. So this is where we're going to go to our fast step. So I'm going to write a rate law for the fast step, and I'm going to write 1 in the forward direction, and it's going to be equal to 1 in the reverse direction. So for step 1 in the forward direction, the rate is equal to my rate constant, and I'm going to give it a little subscript of 1 to show, okay, this is my step 1 rate constant, and then there are 2 NOs, so it's going to be NO squared. And that is equal to my reverse rate. So I'm going to look at the products now, and I'm going to say K, and I'm going to use the subscript -1 to show that it's step 1 still, but now it's the opposite direction. That's where that negative comes from. And it is just the N2O2. Okay. So now if I want to replace the N2O2 in my rate law, my red rate law there, what I need to do is get the N2O2 by itself. So I'm going to divide by K minus 1. K minus 1, so it cancels there. And now my N2O2 is equal to K1 over K minus 1 times the NO squared. So I'm going to plug this piece here in for N2O2 because it's equal to N2O2. So rate is equal to K. And then I'm going to do K1 over K minus 1 NO squared BR2. Okay. All of these K's here are going to combine to one rate constant. So I'm going to rewrite this, my final answer here. Rate equals K, and that's going to be combined of all those individual rate constants. NO squared and BR2, which matches, oh, this should be a 2 down here, you guys, sorry, which matches the rate law that we had experimentally observed. Okay, guys, so this is kind of an involved process to do that fast initial step. So first you're going to write your slow step rate law, and then you're going to create that kind of equality with your fast step to plug in for the concentration of your intermediate. You have 2 practice problems on your reaction mechanism worksheet where you can try this out. Let me know if you have any questions. As always, email me or set up a Google Hangout.